In the lectures so far, we focused on computer vision as it was studied and practiced before the advent of deep learning. Deep learning has completely revolutionized how computer vision is done today. While there have been several dimensions to the efforts in computer vision before this advent of deep learning, hopefully the few lectures that we've had so far gave you a peek into all those efforts, some of which continue to be relevant today when combined with deep learning especially. Moving forward, we'll focus our lectures on deep learning and its use in computer vision. We'll start with the first lecture as a review on neural networks. For those of you that may have done a deep learning or a neural network course before, this may be a review, but even if you have not done such a course before, all the introductory material will be covered in these lectures. I'd like to acknowledge that most content of this lecture are based on the excellent lectures of Mitesh Thapra on deep learning at IIT Madras. To start with the history of neural networks, the history of neural networks is perhaps older than the history of computing itself. It started in the early 1940s when two researchers, McCulloch and Pitts, worked on developing a computational model of the human brain and being able to use that model to simulate simple functions such as logic gates. Later in the 1940s was a psychologist named Donald Hebb who came up with what is known as Hebbian learning, which is used to this day. Hebbian learning states that in the human brain, two neurons that are wired together fire together, two neurons that are out of sync fail to link. Rather, if two neurons keep getting fired together, the strength of the connection between these two neurons gets better and better over time. While if there are two neurons that rarely get fired together, the strength of their connection becomes weaker and weaker over time. This is a principle that is used to this day. Later in the 1950s, Frank Rosenblatt came up with the first model of the neural network known as the perceptron. The perceptron is the simplest neural network one could have, which has a set of neurons, which is known as a layer of neurons, which receives a set of inputs, acts on them through a set of weights, and then gives an output which is thresholded to get the final decision. Rosenblatt also proposed a learning algorithm to obtain the weights in this simple neural network. In the early 1960s, this learning rule was improved by Widrow and Hoff, which is known as the Widrow-Hoff learning rule or the delta learning rule. This was the foundation of algorithms that we use to this day, which we will talk about soon. However, Rosenblatt claimed that this perceptron could classify any kind of a data setting, a binary classification setting. Minsky and Papert, two researchers at that time, disproved this using the example of the XOR gate, which clearly cannot be separated by a simple perceptron. This led to a downfall of neural networks in the 1970s because all the hype of the perceptron had simply been crashed because of its inability to handle the XOR scenario as well as similar complex functions. In the 1980s, the interest once again revived with the development of neocognitron in 1980, which is largely considered as the first version of a convolutional neural network. And in 1986 was the development of a groundbreaking algorithm, backpropagation, which we use to this day by Rumelhart, Hinton, and Williams. Later in the 1980s and the mid-1990s, versions of neural networks such as convolutional neural networks were developed at that time, and these neural networks were adopted in various different applications. One popular application at that time was the handwritten digit recognition problem, which is today known as the MNIST dataset. The reason for the popularity of this dataset was the application setting at that time, which was a requirement of the United States Postal Service, where they wanted the handwritten digits on postal mail to be automatically sorted by an analysis of the digits on the postal card. Convolutional neural networks was one of the forerunners at that time of performance on the USPS or the MNIST dataset. In the mid-90s also came the support vector machines or SVMs, which was backed by an elegant theory and also started performing very well on these applications. And for a large part between the mid-90s and perhaps the first decade of the 21st century, machine learning applications were dominated by what today are known as traditional machine learning algorithms such as support vector machines, boosting, bagging, and many other variants of these decision trees, many other variants of these algorithms. In the mid-2000s, Geoffrey Hinton and Ruslan Salakutdinov came up with a hierarchical feature learning algorithm, also known as unsupervised pre-training, using which they could initialize the weights of a deep neural network, and they showed that this could give distinct advantages of neural networks to outperform other methods. That was the seed of the deep learning revolution. In the years following, there were further efforts to improve the training of deep neural networks. Until then, neural networks could not be trained with many layers, which seemed to be a major limitation. This culminated in the development of the AlexNet, developed by Alex Krzyzewski in 2012 to win the ImageNet challenge. The ImageNet challenge is a dataset consisting of about 1,000 categories, images consisting objects of 1,000 categories with over 1 million images at that time. And AlexNet outperformed all competitors by a significant margin in 2012, taking the entire attention of the computer vision community. Since then, every year's winner of the ImageNet challenge has been a deep neural network. Not only the ImageNet challenge, but even other benchmark challenges in vision have largely been dominated by deep neural networks. And that has led to the golden age for deep neural networks, which we hope to see over the rest of this course. Starting with the McCulloch-Pitts neuron, McCulloch was a neuroscientist and Pitts, who was a logician, proposed a simple computational model of the neuron in 1943. And the way this model worked was, you have a function g, which aggregates a bunch of inputs, which were all binary inputs at that time, and a function f that took a decision based on the aggregation. So the inputs at that time were considered to be excitatory, or 1, or inhibitory, a 0 or a -1, depending on what notation you choose for binary numbers. So your g function was denoted as summation over each of your xi's, and your final output y was given as f of g of x, where the vector x denotes n different dimensions in the in the input space, which was given by 1 if g of x was greater than a threshold theta, and 0 if g of x was less than that same threshold theta. This is what is illustrated here on the right. So you have a set of n inputs. They all come into the function g, which aggregates them, and f is the function that acts on g based on a pre-specified threshold theta. And that decides the final output, which also is a binary value. Here are a few examples of how the McCulloch-Pitts model of the neuron can be used to simulate different logic gates. Here is the basic simple McCulloch-Pitts neuron. Here is the McCulloch-Pitts neuron as an AND function. So you have x1, x2, x3 which are aggregated, and a threshold which is chosen to be 3. So the theta on the previous slide is chosen to be 3 here, which means this neuron, McCulloch-Pitts neuron, would give an output 1 only if all the 3 inputs were 1, because that's when it would exceed the threshold 3. A simple example of an AND gate. Similarly, you could use a similar approach to simulate an OR function where the threshold would be 1 if either of x1, x2 or x3 is a 1. This condition, this threshold would be satisfied and you would get a 1 as the output. And for the NOR function, you have the McCulloch-Pitts neuron to be something like this, where if you notice there is a slight change in notation, and these inputs now designate that these are inhibitory inputs and not excitatory inputs, which means if one of them is on, it's definitely going to give an output as 0. And you can clearly see that as long as the threshold is greater than 0 here, you would get an output. Similarly, the NOT function is another setting where you have a single input and it's an inhibitory input, and if you keep the threshold as 0, you get your output to be 1 to simulate the NOT gate. As you can see, you can probably simulate most logic gate functions using the McCulloch-Pitts neurons. In fact, it's possible to show that not a single McCulloch-Pitts neuron, but a network of McCulloch-Pitts feed-forward neurons, which means you take an input and feed forward that input through a set of McCulloch-Pitts neurons. You can compute any Boolean function, f, that goes from a Boolean input in n dimensions to an output that's Boolean in 1 dimension. Rather, which means if you had, from a machine learning parlance, if you had an n-dimensional input and the output is a binary classification problem, you could solve it as long as your inputs and outputs were all binary. Earlier work has shown that recursive McCulloch-Pitts networks can actually simulate any deterministic finite automaton. We are not going to describe that here, but if you're interested, you can look at this work to understand this connection between neural networks and automata in computer science. As I just mentioned a few minutes ago, Frank Rosenblatt, who was a psychologist, proposed the perceptron model in 1958. This was much later, in the later part of 60s, very carefully analyzed by Minsky and Pepper, who concluded that this cannot work in certain settings. But before we go there, let's introduce what a perceptron is. A perceptron was a generalization of the McCulloch-Pitts neuron, and now the inputs were no longer limited to Boolean values. You could have any real value as input to a perceptron. In addition, each of these inputs were weighted by a set of values which are denoted as W1 to Wn, which means mathematically your perceptron is going to look like you have your G function, which was what we had with the McCulloch-Pitts neuron. which takes an input vector x of n dimensions. Once again, this could be any n dimensions in any data. You could be looking at a patient record, and you may want to say whether the patient is at a risk for cancer. So each of these attributes could be, say, the patient blood group, the patient's age, so on and so forth. Right? Any real value, not just binary values anymore. And the output of the G function is wi xi, an inner product between a vector w and the input vector x. And the final output is again f of g of x, which is going to be 1 if g of x is greater than a threshold, or 0 if g of x is less than a threshold. As you can see, it's a generalization of the McCulloch-Pitts neuron, where the inputs could be beyond Boolean and there are weights which multiply the inputs. A more general way of writing a perceptron is where the index starts at 0 instead of 1, and the 0 is simply to subsume the threshold on as the part of the equation itself. Rather, you're now going to have I is equal to 0 to n, where x0 is going to be 1. It's a constant input 1 all the time. Today this is also known as bias. So if you look at a perceptron as modeling a line, remember the equation of a line can be written as w is equal to, say, w x plus b, where each of w and x can be a vector of a certain dimension, say d dimensions. So b is the weight w naught that we are talking about, which is multiplied by the value 1. That is now subsumed into a common summation which goes from I is equal to 0 to n, where w naught is going to be denoted as minus theta, and the x corresponding to w naught, which is x naught, will always be 1. Why do we do it? The reason we do it is now your output y, which is f of g of x, will be 1 when g of x is simply greater than or equal to 0, and 0 if g of x is less than 0. Earlier, we had, instead of 0, we had theta, which was the threshold. We are now subsuming that on the left hand side of that equation. Inside the g of x, we are bringing the theta, which means now g of x will be the old g of x. Let's call that g hat of x minus theta. So that minus theta is now written as w naught, which is minus theta, into x naught. So this is minus theta and x naught is 1, which is what contributes to this minus theta. So this is a more accepted convention of writing out a perceptron. Let's now look at how the weights of the perceptron are learned. So you have a set of weights w0 to w1. You have a set of inputs 1 and then x1 to xn. Remember, 1 corresponds to the input for the weight w0. You have an input with, say, certain labels with label 1. Let's call that set of inputs to be the positive class, or P. And you have another set of inputs with a label 0, which let's call that class as the negative class, or the set n. We start by initializing the vector w randomly, and then we loop over a set of steps. Let's see what they are. The first step says randomly pick a point, an input data from P or N. Rather, you select X coming from P union N. If X belongs to P, which means it's a positive class, and if your output was less than 0, remember, for a positive class, you would have wanted your output to be greater than 0. But if it is less than 0, you simply add X to W. Why is this so? We'll see in a moment. And if X belongs to the negative class and your output turned out to be positive or non-negative, it could be equal to 0, you once again do subtract X from W. Now you could ask the question, what about the scenario where X belongs to P and Wi Xi, the summation, is greater than or equal to 0? You simply don't do anything in that particular scenario. Same case with X belonging to N and the summation being less than 0. You assume things are good and don't worry about the weights in those scenarios. Now we have a termination criterion here which says until convergence, keep doing this. So how do you converge? You converge when all of your inputs are classified correctly by the W's that you have. What does classified correctly mean? For all your data points P, the output of your perceptron was greater than or equal to 0. And for all your inputs coming from the set M, the output of the perceptron is less than 0. Okay? That's the overall idea of the perceptron learning algorithm. But now let's ask the question, why would this work? Why should we add X to W? Why does that constitute a learning procedure and why would that improve the quality of W? Let's see that a bit more carefully. Remember, as we said on the previous slide, that a perceptron is a model of a line because it's effectively Wx plus B, where the B gets subsumed as W0. So it's the equation of a line, right? And the line's equation is given by summation I going from 0 to N. Wi Xi is equal to 0. This line divides your input space into two halves. The half of inputs where Wi Xi will be less than 0 and the half of inputs where Wi Xi, the summation over Wi Xi, will be greater than or equal to 0. Every point on that line satisfies the equation W transpose X is equal to 0. Remember, whether we say W transpose X is equal to 0, this is equivalent to saying inner product of Wx is equal to 0, which is equivalent to saying summation over I Wi Xi is equal to 0. Okay? This is something that we'll keep interchangeably using for the rest of this course. But please keep in mind that whether we say W transpose X or W dot X or summation Wi Xi, all of them mean the same thing. We know now that every point X on that line has to satisfy the equation of that line, which means W transpose X has to be 0. Now, what can you tell about the angle between W and any point X which lies on that line? This comes from geometry. The angle will always be 90 degrees. Rather, for the equation of any line, let's say you take the equation of any line which is given by W transpose X. Okay, remember once again that the intercept B is going to get subsumed into W naught. The vector W will always be perpendicular to the line. Why is that the case? Because you have cos alpha. So if you take a point X here, okay, let's take a particular point X on this line. The angle between X and W, which is say given by alpha, is given by W transpose X by norm W norm X by simple expansion of the dot product. Okay. And that angle we know has to be 0 because W transpose X has to satisfy 0 for all points on the line, and hence the angle has to be 90 degrees. Rather, the vector W is perpendicular to points on the line. Why does this matter? Now let's look at a point belonging to class P. Remember, this point does not lie on the line. It lies on the, you want it to lie on the side of the line where W transpose X is greater than or equal to 0. Because it belongs to the positive class, you want your perceptron to classify this point correctly, which means the perceptron should give you a value greater than or equal to 0. Let's see what it would be. If you want the perceptron to classify this point correctly, the angle between the vector x, p and w has to be less than 90 degrees. Why so? Let's again write out that line. This is the line which is given by w transpose x. Remember, this is w, this is the set p, this is the set n. Okay, so all the input points which have a negative class are on one side of that line. All the input points which are on the positive side of the line belong to the positive class. So now any point in the positive class lies somewhere here, which means its angle is now going to be less than 90 degrees. Similarly, what about the angle between the vector x belonging to a negative set and w? This should be straightforward. It has to be greater than 90 degrees for the same way we visualized the positive class a minute ago. You can, if you don't get it, you can spend a couple of minutes, draw it, and you will see that this should work out. Now, if you have a point x belonging to p for which w transpose x becomes less than 0, it means that the angle alpha between this x and the current w is greater than 90 degrees, which you do not want it to. You want to change w to ensure this doesn't happen, but currently it's greater than 90 degrees. So what do? We want it to be less than 90 degrees. So we are saying that we are going to add x to w to achieve this purpose and make the angle between w and this x belonging to p less than 90 degrees. Why do you think that helps? Let's understand that. Let's consider this w new to be w plus x, which means we have added that x which belonged to p to w and got a new w in the next iteration. Let's try to understand what the new angle will be. We just found out that when w transpose x is less than 0 for a point belonging to p, the angle turns out to be greater than 90, which we don't want. We want it to be less than 90. Now let's see what happens for w nu. We know that cos alpha nu is equal to w nu transpose x divided by the norm of each of those two vectors, w nu and x. So we are going to ignore the denominator and simply say it's proportional to w nu transpose x, okay, which can be said is proportional to w plus x transpose x, because w nu is equal to w plus x, which can be written as w transpose x plus x transpose x, which can be written as cos alpha, because we know that w transpose x is proportional to cos alpha plus x transpose x, which means because x transpose x has to be a positive quantity, because it's a dot product of a vector with itself, so all values will get squared and you will add up all of those values. You know that cos alpha nu has to be greater than cos alpha. Rather, this tells us that alpha nu, which is the angle, will be less than alpha, and hence we are going to get the right weight vector, which will ensure that points belonging to P have the output of the perceptron to be greater than or equal to 0. But you can work out a similar scenario for points belonging to the negative class, and you will get a negative class where the output of the perceptron is greater than or equal to 0. You can work out a very similar scenario. The only thing is you would have a negative sign here, and you will find that the new angle will be greater than the old angle, which is what we would want for a negative class. That should convince you that this perceptron learning algorithm will keep improving in each iteration. Now, when would it converge? We only know that it would keep improving. The W that you get through this algorithm will keep improving in each iteration. But whether it will get us to that final solution, we still have not shown, and we're probably not going to work out that detail here. But if you want a formal convergence proof to show that as the number of data points increase, as the number of iterations increase, you are going to get a solution as long as you can separate points originally into two classes P and N using a line. You can see it. This link shared here for the formal convergence proof.